Good morning guys. Today we'll start with the very important chapter, that is your mechanical properties of dental material. So it is very important for your exam point of view. These are the contents. Starting with the introduction. In the oral environment, restorative materials and the dental appliances are exposed to chemical, thermal and mechanical challenges. So basically there are three types of challenges, that is your mechanical, your thermal and your mechanical challenges. So basically these challenges can cause the deformation of the material. The mechanical properties of a material is defined how material responds to the mechanical changes. So mechanical properties are defined by the laws of mechanics. That is, it is the physical science that deals with the energy, the forces and their effects on the body. So basically, what does your mechanical property means? It means that it is a physical science which basically deals with the energy, the forces and their effect on the bodies. Starting with the viscosity, it is resistance of a liquid to flow. Thus, viscosity is measure of a consistency of the fluid and its resistance to flow. Study of the flow characteristics of the material and the deformation is known as rheology. The term rheology was coined by Bingham. So, what do you mean by rheology? It is the study of the flow characteristics of the materials and the deformation. So, clinical implication of the viscosity in dentistry. It is important to have a low viscosity molten metal during the casting in order to completely fill the mold. Impression material should have a sufficient degree of fluidity to get the details and also the fairly complex areas of the tooth structure. So changes of the viscosity of an impression material with time is important. To explain the viscosity, we have your curve plotted, your shear stress and the stress and strain curve, you can say. So this is your pseudoplastic, this is your Newtonian, dilatant and your plastic. Coming on to your Newtonian fluid, that is also known as the constant fluid. So it is an ideal fluid. So in this, the shear stress is proportional to the strain rate. A straight line on the curve. Can you see this? A straight line, Newtonian, a straight line on a stress and strain graph. Viscosity is equal to shear stress by shear rate, and it is having the constant velocity. The example of Newtonian, that is your constant fluid, is water and zinc phosphate. Coming on to the pseudoplastic fluid, in this the viscosity decreases with increasing the strain rate until it reaches a nearly constant value. So can you see this? It is nearly a straight line until it reaches to its normal value. Can you see the bend over here? It is straight line, and after some point until it reaches the near constant value, it is having a straight line. After then it gets deformed, or you can say it gets slightly bent. So example is the monophase elastomeric impression material. Coming on to the dilatant fluid, in this the viscosity increase with the increasing stress. In this the viscosity increasing with the increasing stress rate. It is dilatant. So example is the acrylic denture bases, your material, sand in water. So disadvantage of your dilated fluid is, in this the material becomes more rigid under the stress. Coming on to the plastic fluid, in this the material behaves rigid until a minimum of stress is applied. Then it starts behaving like Newtonian fluid. Newtonian fluid was like a straight line. Can you see this? Newtonian fluid was a straight line plotted in your stress or strain curve graph, and the plastic is somehow equal to your Newtonian fluid. Okay, so in this the material behaves rigid until a minimum of stress is applied. Then it starts behaving like a Newtonian fluid. So example is your clay suspension and the composite material. Coming on to the creep and the flow. So creep, as I've already told you in the chapter of dental amalgam, that creep, it is a time dependent plastic deformation which occurs when a material is subjected to a constant load near its melting point. I had already told you in the dental amalgam chapter. So creep is defined as a time dependent plastic strain of a material under a static load or a constant load. The term creep implies a relatively small deformation produced by a relatively large stress. Can you see this? It is the normal and this is your distorted. This is your creep and your flow. Can you see this? The thickness of your restorative material. It is due to the large stress or the heavy stresses. So creep is a property applied to a solid material or the metal like the amalgam. Same way in this. Metal creep usually occurs at a temperature increases to within a few hundred degrees of the melting rate. As what do you mean by creep? I have told you that it is a time dependent plastic deformation which occurs when a metal is subjected to the constant load near its melting point. When you increase the temperature of a material above its melting point, it leads to creep. Ceramic does not have creep because to the higher forces of the atomic structure. So these materials show crack and fracture when subjected. Coming on to the clinical significance, creep may cause unacceptable deformation of a dental restoration, as you have seen in this slide. Deformation. It may also lead to unacceptable fit of an RFPT, that is the fixed partial denture, when a cast allow with the porcelain at high temperature. Coming on to the flow, the property of a material to deform when subjected to stress. The flow of wax is a measure of its potential to deform under a small static load, even that associated with its own wax. So type 1 inlay wax show flow of 90%, that is marked flow above the mouth temperature that is required to mold the wax for making wax pattern. The temperature above your mouth temperature. So at the room temperature, these waxes show flow of 1% that permits removal of the wax pattern from the mouth. At the room temperature, these waxes show 1% of flow, and above the mouth temperature, these waxes show 90% of the flow. Flow implies a greater deformation produced more rapidly with a smaller applied stress. The term flow is generally being used in the dentistry to describe the rheology of the amorphous materials such as waxes. So flow is basically used in the dentistry to describe the rheology of your amorphous material such as your waxes. Coming on to the very important part, the color and the color perceptions. So what is color? Color is a sensation induced from the light of varying wavelength reaching the eye. So as you all know that our eyes carry two cells, the rod cells and the cone cells. So the cone cells of the retina are responsible for spectral sensitivity. Sensation induced from the light of varying wavelength reaching the eye. So in this, the cone cells of the retina are responsible for spectral sensitivity, determined visually by measurement of hue, chroma and the value. The three important terminologies. Color perception. The phenomena of the vision can be explained by considering the response of the human eye to light reflected from an object. Light from an object that is incident on the eye is focused in the retina, as you all know. From retina it is converted into nerve impulses which are then transmitted to the brain. So color perception has the three objective variable, that is the hue, your value and your chroma. What is hue? It is defined as a particular variety of a color, shade or the variety or the tint. Example, red, green, yellow. So hue is, what is hue? It is basically defined as a color, or you can say the shade of a color, whether it is red, blue, green, white, yellow, purple. So chroma, it is the intensity of the color, degree of the saturation of a particular hue. Value, it is defined as a relative lightness or the darkness of a color or the brightness of an object. Value of 0, when you add a black or white color to any particular color, it tends to have a relative lightness or darkness of the color. So in that, the value of, when you added more black, the value of 0 is black. When you add more white, the value of 10 is white. Coming on to the hue, it is defined as a particular variety of the color, shade or the tint. This refers to the dominant wavelength present in the spectral distribution. For example, you have yellow color, you have red color. There are different tints of red, different tints of blue, different tints of yellow, green. So this is your hue. It is particularly a color or a shade or a tint. Coming on to the chroma, it is the degree of saturation of a particular hue. Example, red can vary from scarlet to pink. See, this is your red color. It is varied from scarlet, it is more darker, and light pink, it is less red. So it is more red, it is less red. Where the scarlet has the highest, it is having the, this is having the highest saturation point, and this pink has the low saturation. So basically chroma is your saturation of the particular hue. Hue is your color and the saturation of your color is your chroma. So crown is not considered separable in dentistry. It is always associated with the hue and the value of the dental tissue, restoration and the prosthesis. I hope the chroma is clear to you. Basically it is a saturation of a particular hue, that is a saturation of a particular color. So this is different shades of your red. More red, it is the scarlet color. More white, it is the pink color. So in this pink there is a low saturation. In your more red, that is in your scarlet, the saturation is higher. Coming on to the value, it is also known as grayscale. It is vertical or a z-axis, or on a z-axis, value increases towards higher end and decreases towards a lower end. It is also known as black and white. See, in this, amount of black or white is added to color. For example, in your red color, take it as an example, if you are putting more white color in your red, if you mixes more white color in your red color, what you get is, you get a lighter shade. When you mix black color in your red color, what you get is, you get the darker shade. So in this, the value of black, is considered as 0, and the value of white is considered as 10. So it is basically the white and black color is added to your color, and it gives your lighter color, it gives your darker color. Darker ones, the value is 0, the lighter one, the value is 10. These three, as you all know, hue is the position of the colors. For example, yellow, your green, dark green, blue, violet, pink, red. It is basically hue is your color. Value, I've already told you, it is the amount of black or white added to the color. When you add black color in your gray, when you mix your black color in your gray, what you get? You get the darker shade, you get the darker color, which is having a value of 0. And when you add more white into this gray color, it will get lightened, and what you get is, the value is 10. Coming on to the chroma, it is the amount of brightness or the saturation of the color. The shades, you can see the shades of the color. It is more lighter, it is more darker. It is the amount of, when you saturate one color, when you saturate this color, you will get lighter one and the darker one. Coming on to the Munsell color system, it is very important. See, what is this? This is your hue. This is your different color, their tints. This is your hue. Clear? And this is your chroma. Yeah. When you add a white or black color in this, what you get is, when you this is your gray color, when you add more black to it, it gets darker and darker in color, which is having a value of 0. When you add more white color to it, what will get it? White color, lighter color, and the value is 10. So it is your hue, this is your chroma. Coming on to the value, it is the saturation. So this is, can you see this? When you saturate this color, you will get the lighter portion, you will get the darker portion. I hope this Munsell color system is clear to you. So I have one important MCQ regarding this Munsell's color system. The MCQ is, Munsell system, important MCQ, it was there in your AIPG exam. The Munsell system is used to, your answer is, measure different colors quantitatively. I repeat, Munsell system is used to measure different colors quantitatively. I hope it is clear to you. Coming on to the color terminologies, number 1 is the opacity, the measure of the impenetrability of the visible light. You will get nothing when you pass the light. It will never come out from this side. When you pass the light from this side, it will never come out from this side. So it is your opaque. Translucent, diffuse transmission of visible light. When you pass the light from this, the visible light, certain amount of rays coming out, light coming out from this side, or you can say the haziness, or you can say the foggy appearance, you can say it is known as translucent. Opaque is no transmission of light, certain visible light transmission of light, you can see here. and in this transparent, when you pass a ray, when you pass a light, it is completely coming out from the other end. That is known as transparent, that is the capable of transmitting the light. I hope this is clear to you. Coming on to the metamerism, it is a phenomena in which objects appear color matched under one type of light and different under another light source. When you smile in presence of sunlight, the color of your teeth appears different color. When you smile in the presence of your dental light, the color of your teeth will show a different color. So it is known as metamerism. Clinical significance: color matching should be done under a natural light source, that is the sun and the dental chair, or color matching could be done using either white light or the sunlight. Okay, when you matching a shade of your crown in your dental chair, please do not match your crown in the presence of your dental light, in a dental chair light. You can match the color of your prosthesis with the natural teeth. You can, with a Vita shade, you can say Vita shade in the presence of your natural light, not in the presence of your dental chair light. Okay, so as I've already told you, it is a change of the color matching the two objects under a different light. Can you see this? The change in the color, it is known as metamerism. Coming on to the fluorescence, the fluorescent material such as the tooth enamel absorbs near ultraviolet radiation that ranges from 300 to 400 nanometer and then re-emit radiant energy at a lower frequency that it is absorbed. Tooth becomes the source of light and emits the wavelength of 400 to 500 nanometer, that is in the blue or the white region. Ceramic crown and the ceramic agents that lack a fluorescent agent appears as missing teeth when viewed in the black light. See, ceramic crown and the ceramic agent that lack a fluorescent agent, which is not having a fluorescent agent in your crown, ceramic crown and ceramic agent, they appear as a missing teeth when viewed in the black light. So what fluorescence is doing? It is a material, fluorescent is a material as a tooth enamel which absorbs your ultraviolet light and re-emits the light. So in fluorescent light, teeth absorbs the energy and convert it to light with a longer wavelength. Tooth becomes an actual source of light. It emits 400 to 450 nanometer. It is very important for your exam point of view, this range of your wavelength. Coming on to the thermophysical properties. The thermophysical properties can be defined as material properties that vary with the temperature without altering the material's chemical identity. When a restorative materials are placed in the deep cavity, heat transmitted to the vital dental pulp, as you all know, it must be limited so as to prevent the thermal shock and the trauma. While the denture bases its contact with the mucosal surface is desirable to convey sensation of heat and cold associated with the food and the beverages. Such attributes are governed by the property of thermal conductivity and the thermal diffusivity. Coming on to the thermal conductivity, it is defined as a quantity of heat in calories per second passing through a material 1 centimeter thick with a cross section of 1 centimeter square, having the temperature difference of 1 Kelvin, and is measured under the steady conditions in which the temperature gradient does not change. So the international system unit in watts per meter per Kelvin. Materials that have high thermal conductivity are called are called conductors, as you all know, whereas low thermal conductivity are the insulators. I repeat, materials that have high thermal conductivity are called conductors, whereas the material which is having the low thermal conductivity are called insulators. Material that have a high thermal conductivity are called conductor, as I've already told you. So the international system of unit or measure of the thermal conductivity, as I've already told you, it is watt per meter per second per degree Kelvin. The higher the thermal conductivity, the greater is the ability of a substance to transmit thermal energy and vice versa. If the material having a higher thermal conductivity, the greater is the ability to transmit thermal energy to the substance. So these are the density and the thermal properties of your water, enamel, dentine and the dental material. Please go through it once, it is very important. Coming on to the thermal diffusivity, it is the measure of the rate at which the body with no uniform temperature reaches a state of thermal equilibrium. The thermal conductivity of the ZOE is slightly less than that of dentine, and its thermal diffusivity is more than twice of the dentine. So thermal conductivity of the ZOE is less than dentine, but its thermal diffusivity is more than twice of than that of the dentine. So what is thermal diffusivity? It is the measure of the rate at which the body with no uniform temperature reaches at a state of thermal equilibrium. I hope it is clear to you all. Coming on to the coefficient of the thermal expansion, it is defined as a change in the length per unit of original length of a material when its temperature is raised to 1 degree Celsius. So it is basically the change in the length per unit of its original length when the temperature of the material is raised to your 1 degree Celsius. So coefficient of thermal expansion is your change in the length divided by original length into change in the temperature. So the unit is your millimeter, your Kelvin. So it dictates procedure for using wax pattern, casting metal crowns excuse me, placing amalgam and composite restorations, and preparing metal ceramic crowns and bridges. So the high thermal expansion, that is the coefficient of inlay waxes, is important as it is susceptible to temperature changes. The example is excuse me. The example is an accurate wax pattern that fits the prepared tooth contracts significantly when it is removed from the tooth or from the die in a warmer areas and then stored in the cooler areas. This dimensional change is transformed to a cast metal restoration which is made from the lost wax process. Okay, I'm again asking you this question. I have asked you for many a times that who gave the lost wax technique. I hope now it is clear to you guys. So Dr. William H. Taggart gave the lost wax techniques. See, it is very much important. We have read this lost wax technique, in fact, in every chapter, in every topic. So it is very important. Coming on to the clinical significance, the close matching of the coefficient of thermal expansion is important between the tooth and the restorative materials to prevent the marginal leakage. So basically what is the function of it? It prevents the marginal leakage. The opening and the closing of gap results in the breakage of marginal seal between the filling and the cavity wall. This breakage of the seal leads to marginal leakage, which leads to discoloration or the hypersensitivity. Now these are the coefficient of thermal expansion of the dental materials compared with those of the tooth, that is the enamel and the dentine. Now coming on to the force. So what is force? Force, it is any influence that causes an object to undergo a certain change, either concerning its movement, direction or the geometrical construction. So basically force can be push force or a pull force. The force have both the magnitude as well as the direction. So when you apply a force, the object tends to move from its rest position is known as force, whether it is a push force or a pull force. Okay. The force is defined as by three characteristics, that is the point of application, the point from where you apply the force, the magnitude of force and the direction from where you apply the force. So the SI unit of the force, as you know, it is Newton. Maximum occlusal force is 200 to 3500 Newton. Please note it down, it is very important. Occlusal forces between the adult teeth are highest in the posterior region, in the adult teeth closest to the mandibular hinge axis, and decrease from molar to incisor. As you coming from your posterior part to your anterior part, your force, your occlusal force is getting decreased. So force on the first and the second molar are vary from 400 to 800 Newton. Average on the bicuspids, cuspids and incisor, it's about 300, 200 and 150. That is, on your bicuspid it is 300, your cuspid 200, and on your incisor it is 150 Newton of your occlusal force. So increase in the force from 235 to 494 Newton in growing children, with an average yearly increase of about 22 Newton. Very important slide. Please remember these values, it's very important. Now coming on to the stress and strain. What is stress? The force per unit area acting on millions of atoms or molecules in a given plane of material. So basically it is a force per unit area. Force acting per unit area. Stress is your force by area. Force, the SI unit of force is Newton and your area is millimeter square. The unit of measurement is megapascal. The stress is the internal resistance of a material to an external load applied on that material. So types of stresses produced by: residual stress, the stress caused within the material during the manufacture process, example during the welding. Structural stress, stresses produced in the structure during the function. Weights they support provide the load, example in your abutments, in your FPDs. Pressure stress, it is induced in the vessels containing pressurized material, for example in your dentures, during the process under pressure and heat. Flow stress, it is the force of liquid striking against the walls act as the load, example in your molten metal alloy that striking the walls of your mold during casting, as I've already told you about this in your casting procedure. So thermal stress, it is a material in this the material is subjected to internal stress due to different temperature causing varying expansions in the material. So it is used in the material that undergo thermal stress, that is your inlay wax, your soldering and your welding alloys. Fatigue stress, it is a stress caused due to cyclic rotation of the material, that is your rotary instrument, when they undergo the rotational and the cyclic fatigue. By means of the direction of the force, stresses can be classified as tensile stress, compressive stress, shear stress, and the flexural stress. So tensile, compressive, shear, and your flexural stress. Coming on to the tensile strength. The tensile strength occur when the two set of force are directed away from each other in a same straight line. Also, when one end is constrained and other end is subjected to force away from the constrainant. What the tensile force does is, it is caused by a load that tends to stretch the or elongate the body. When you apply a force, one from this side, one for this side, what will be done is, what is going to be done in this? It will get stretched. Example, see, I'm giving you a simple example, is the rubber band. When you stretch it, you can apply the force from one direction, the pull force from another direction. What you get is, you get the stretching of your rubber band. It is known as your tensile stress. So in the fixed prosthetic, a sticky candy can be used to remove the crowns by means of the tensile strength. When the patient tries to open the mouth after the candy has mechanically bonded to the opposing teeth and gums, which helps to remove the crown with the help of your tensile strength. Coming on to the compressive strength, this is the stress occur when the two sets of forces are directed towards each other in the same straight line, and it is caused by the load that tends to compress or shorten the body. Same way, in the tensile strength, you apply the force from this direction and from this direction. What you get was, you elongate or you stretch the body. In this, you shorten or compress the body, because you applying the force one from this side and one from this side. What you get? You get compressed force. You compress the material and simultaneously it gets shortened also. Coming on to the shear stress. The shear stress occurs when the two sets of forces are directed parallel to each other but not along the same straight line. Shear stress tends to resist the sliding of one portion of the body over the other. So shear stress can be produced by twisting or the torsional action on the material. So in this, you are applying a force not in a same straight line. You are applying the two sets of forces directly parallel to each other but not in a straight line. So what you get is, you get a twisting or a torsional action. So it is the debonding plier. In an orthodontic, we use to debond the bracket with the help of the debonding plier. So if a force is applied along the surface of the tooth enamel by a sharp edge, the debonding plier having the sharp edge, it is helped to debond the bracket from the tooth and take it out. Instrument parallel to the interface between the enamel and the orthodontic bracket. So the bracket may debond by shear stress, failing of the resin luting agent. So what you have to do is, you just apply, this is the sharp end of the debonding plier. When you apply this sharp edge at the interface between your enamel and your orthodontic bracket, you can apply this on this particular point, and you just need to press these two. When you press, the bracket will come out from the tooth. So in the oral cavity, shear failure is likely to occur due to many of the brittle materials in restored tooth. Surfaces generally have a rough and the curved surfaces. The presence of chamfers, bevels, or change in the curvature of a bonded tooth surface. To produce a shear failure, the applied force must be located immediately adjacent to the interface. As I've already showed you, you have applied the force between enamel and the tooth bracket interface. When you apply the force, it will come out. So the farther away from the interface the load is applied, more likely that it is a tensile failure. Obviously, when you not applied a proper force at the interface, if you are applying any force away from the interface, you will definitely get a tensile failure. Since the tensile strength of the brittle material is usually well below their shear strength values, tensile failure is more likely to occur. Coming on to the flexure stress, it is also known as bending of your object. So force per unit area of a material is that subjected to flexural loading, that is bending. A shear stress tends to resist the sliding of one portion of a body over the other. The flexure force can produce all the three types of stresses in a structure, but in most cases fracture occurs due to tensile component. What basically we are doing in this is we bend the material. The flexure stresses is or the bending type of force we apply. It is basically, you can see this in your fixed partial dentures when you're giving your FPDs. See, the flexure stress produced in a 3-unit fixed dental prosthesis. This is the compression force. You can say the chewing force or the compression force. Okay, see, your compression force is doing what? It compresses from the occlusal surface. When it compresses your FPD, what is caused is, it is caused the tension. Your flexure bending, you can see flexure stress, you can see the bending of your FPD from this side. Same way, when you have a 2 cantilever bridge, this is your compressive force. In this compressive force, you can see the bending or your flexure stress, the bending of your 2-unit FPDs and 3-unit FPDs. Coming on to the strength. The strength of a material is defined as an average level of stress at which a material exhibits a certain amount of plastic deformation, or at which the fracture occurs in several test specimens of the same shape and the size. So, in this clinical, the strength of the brittle material, that is the ceramics, the amalgams and the composite, may appear to be the low when large flaws are present. When the large flaws are present, you can get the fracture, or if the stress concentration areas exist because of improper design of the prosthetic component. So under these conditions, such appliances may fracture at a much lower applied force because the localized stress exceeds the strength of the material at a critical location of the flows or the stress concentration. If we, for example, in this, it may get, why it get fracture? Because the stress which exceeds the strength of the material at a critical location, and what you get is stress concentration. So the strength of the material is not that much high, so the localized stress is continuous poking at this area and it will cause the fracture. Either it is the fracture you can see on the dental restoration, that is on the amalgam restorations, or your composites and in your ceramics. So elastic stress is ductile. Materials such as gold, as you all know, do not cause any permanent damage. So plastic stresses does cause permanent deformation, and sometimes it may be high enough to produce a fracture. It is the plastic stresses. Since the stress in the structure varies directly with the force and inversely with the area over the force act is important into consideration. See in this picture, can you see the area of the restorative material, your cusp, when considering as the dental restorative material, when the area over the occlusal forces act as are the extremely small as the cuspal area of the contact. In this, your occlusal forces, where it is acting, your occlusal forces are acting on your incisal edges or your cusp tip. Can you see this? Coming on to the strain, it is defined as a change in length per unit original length. The strain of a material is reported as percentage. The strain may be either elastic, plastic, or a combination of both elastic and the plastic. Very important, elastic strain is reversible. That is, it disappears when force is removed. It came back to its original shape. Plastic represent permanent deformation of a material which never recovers, or when the force is removed, it never tends to its normal position or the shape. A tensile force is 200 Newton is applied to an orthodontic wire of the cross-sectional area of this. If the wire is 0.1 m long and if it stretched to 0.001 m under the load, the wire will fracture at a tensile strength of 100 megapascal and a tensile strain of 0.01%. See, it is the elastic deformation, it is the plastic deformation. When you applied a force, that is a shear force of any kind of force, when you apply it, it will get elongate. But when you release the stress, when you release the force, it will tend to come into its normal position. It will not get distorted. But when you apply the same force in the plastic deformation, when you apply the same force, it tends to get deformed. So when you release the force, it will get deformed only. It will never get back to its original shape or original form. So this is the main difference between the elastic deformation and your plastic deformation. There is a permanent deformation, there is no deformation in the elastic, and there is a permanent deformation in the plastic. So stress strain curve, as you all know, this is the elastic modulus, it is your proportional limit, this is your yield strength, and this is your ultimate tensile strength. Coming on to the mechanical properties based on the elastic deformation. Mechanical properties that are measure of the elastic strain of the dental material includes your Young modulus or the modulus of elasticity, dynamic Young modulus, Shear modulus, flexibility, your resilience, and your Poisson's ratio. Coming on to the Young modulus, the elastic modulus describes the relative stiffness of a material, which is measured by the slope of the elastic region of a stress strain graph. If the stiffness of a material, that is calculated as a ratio of the elastic stress to strain, that is, stiff material will have high modulus of elasticity, while the flexible material have the low modulus of elasticity. Please keep this in mind, that your flexible material having the low modulus of elasticity, whereas your stiff material having the high modulus of elasticity. So elastic modulus of a tensile specimen can be calculated by the definition. You can say this is your force by area, and this is your original length by your change. This is your change in the length by your original length. See, this is the steeper line. this is the flat line. This is having the low modulus of elasticity. Can you see this? This is the low modulus of elasticity, and because these are low modulus of elasticity means these are which material? I have already told you. The flexible material. So these are basically the flexible materials, and the steep line, the steep, you can see this is the flat, yeah, see, this is the stress strain curve, this is your proportional limit, this is your elasticity, Young's modulus of elasticity, and ultimate tensile strength. So steep line means higher modulus of elasticity, and your flat line means lower modulus of elasticity. Example, the principle of elastic recovery. So burnishing of an open metal margin where a dental abrasive stone is rotated against the metal margin to close the marginal gap as a result of plastic and elastic strain. Can you see this? It is a dental abrasive stone. It is rotated against the rotated against the metal margin to close the marginal gap. So after force is removed, the metal springs back to the amount equal to the total elastic strain, and the final clearance of 25 micrometer is available for the cement. So example, impression material. The impression material should have a low modulus of elasticity to enable it to remove from the undercut areas in the mouth. So it has the low modulus of elasticity, so it is a flexible material, but the modulus of elasticity is not very low that the material cannot withstand the tearing. Important. Coming on to the Hooke's law. According to this law, within the limits of elasticity, the strain produced by the stress is proportional to the stress. The stress at which the material ceases to obey Hooke's law is known as the limit of proportionality. The Hooke's law can be expressed by the formula. The value of the constant depends on the material and the type of stress. So basically this is a stress strain curve between the enamel and the dentine. This is your enamel, this is your dentine. In your dentine, it is capable of sustaining plastic deformation under a compressive load before it get fractures. So in this, it is susceptible, you can say it has a significant plastic deformation. Can you see this? When you apply a force to this, after a certain amount it will get distorted. It is known as plastic deformation. And in the enamel, it is more stiffer. Enamel is more stiffer than, see, it is an example of your plastic deformation. Plastic deformation is, I have told you that when you applied the force, after certain extent, when you remove the force, the object will get distorted. When you remove the force, it will not come back to its original form or in shape. So in this, when you apply the force, it is capable of sustaining a significant plastic deformation. After this, it tends to get deformed. When you remove the force, it will not get back to its original form. So enamel, it is more stiffer and brittle than dentine. It is more stiffer, so it has more elasticity. So but dentine, it is more flexible, so it is a low modulus of elasticity, but it is tougher. Coming on to the Poisson's ratio, during the axial loading in the tension and the compression, there is a simultaneous strain in the axial and the transverse or the lateral directions. Under the tensile loading, as a material elongates in the direction of the load, there is a reduction in the cross-section area. When you apply the force, there is a reduction in the cross-section area. Under the compressive loading, there is an increase in the cross-section. When you applied a compressive force, there is an increase in the cross-section area. Can you see this? When you applied your compressive force, you apply a force from the top, you apply a force from the bottom. What it does is it increases the compressive area. It gets shortened, but it gets wider. So there is an increase in the cross-section area. When the elastic range, the ratio of the lateral to the axial strain is called as within the elastic range, the ratio of the lateral to the axial strain is called as Poisson's ratio. The Poisson's ratio is a unitless value since it is a ratio of two strains. The most rigid materials such as the enamel, dentine, amalgam, composite exhibits a Poisson's ratio of about 0.3. More ductile materials such as soft gold alloys show a higher degree of reduction in the cross-sectional area and it exhibits a higher Poisson's ratio. Coming on to the dynamic modulus, Young's modulus, it is the elastic modulus that can be measured by the dynamic method as well as the static method. Static means the rest method, dynamic means moving method. So the velocity at which the sound travels through a solid can be readily measured by ultrasonic transducers and the receivers. So as you all know, the velocity of the sound can be measured from the ultrasonic transducers and your ultrasonic transducers and your receivers and your transducers. So the velocity of the sound wave and the density of the material can be used to calculate the elastic and the Poisson's ratio. So if a shear stress was induced instead of a uniaxial tensile or a compressive stress, the resulting shear strain could be used to define a shear modulus for the material. So it can be calculated as your elastic of modulus. Okay, that is your shear modulus, and this is your elastic of modulus, and the ratio is known as your Poisson's ratio. So the value of 0.25 to 0.30 for the Poisson's ratio is typical. Therefore, the shear modulus is 38% of the elastic modulus value. Coming on to the flexibility, as you all know, the term itself indicate what do you mean by flexibility. So it is a flexural strains that occur when the material is stressed to its proportional limit. The material used to fabricate dental appliances and restoration, a high value for the elastic limit is necessary as a requirement. This is because the structure is expected to return to its original shape after it has been stressed or forced removed. As you all know, for example, you can take it as a spring, the very good and very nice example of the flexibility. The maximum flexibility, the flexural strain that occur when the material is stressed to its proportional limit. See, there are instances where a large strain or the deformation may be needed with a moderate or the slight stretch, such as the orthodontic appliance. See, this appliance is known as the quad helix appliances. This is mainly used for your expansion of your arch, and you can say for the correction of your posterior crossbite. So this is the quad helix because it has the 4 circles. It is known as the quad helix, and this portion, this arm will create a push pressure. It will push these 3 teeth these 3 segments your buccally, so that what you achieve is number 1, your crossbite should be corrected, number 1, and you will get an expanded arch. Okay, second, it is known as your Z spring. It is also used in the orthodontic. It is also used as an orthodontic appliance. It is known as a Z spring. It is mainly used to correct your anterior crossbite. This arm will apply a push force to this tooth, that this particular tooth will get flare, or you can say this particular tooth will procline, and your anterior crossbite is corrected. So it is known, this is the removable appliance, orthodontic appliance. So it is basically used to correct the anterior crossbite, or you can say the single tooth crossbite. Coming on to the resilience, it is the amount of energy per unit volume that is sustained on loading and released upon unloading of the test specimen. I'm sorry, this is the main example of the spring. I was confused with that resilience and this flexibility. So flexibility is it is a flexural strain that occurs when a material is stressed to the proportional limit, and in this there is loading and releasing upon the specimen. The term resilience is associated with the springiness of a material, but it means precisely the amount of energy absorbed within a unit volume of a structure when it is stressed to its proportional limit. In this, the amount of energy absorbed within a unit volume of a structure when it is stressed to its proportional limit, and in this, when the material is stressed to its, is a flexural strain. Okay, that is the bending. I have told you in this. I have told you in this the fractional stress, or it is known as bending. Okay. So basically, your flexibility is defined as the flexural strain, that is the bending that occurs when the material is stressed to the proportional limit. And in this, your resilience, in this, it is the amount of energy which is sustained on loading and release upon unloading the specimen, for example the spring. The term resilience is associated with the springiness of the material, but it means precisely the amount of energy absorbed within a unit volume of a structure when it is stressed to its proportional limit. So resilience of two or more materials can be compared by observing the areas under the elastic region of their stress strain graph. That is, the material with the longer elastic area has the higher resilience. The material with the longer elastic area, can you see this, has the higher resilience. When the dental restoration is deformed during mastication, it absorbs energy. If induced stress is not greater than the proportional limit, the restoration is not permanently deformed. If your induced stress is not greater than that of your proportional limit, so your restoration will not get deformed. That is, the only elastic energy is stored in it. So the restorative material should exhibit a moderately high elastic modulus and a relatively low resilience, very important, which limiting the elastic strain produced. So basically, if your restoration in your restoration, if your induced stress is not greater than your proportional limit, your restoration will never ever get deformed. So chewing force on the dental restoration causing deformation. Large deformation does not occur due to proprioceptive receptors of your periodontal ligament. So the pain stimulus causes the force to decrease and induce the stress to be reduced. This prevents the damage of the tooth or the restoration. So this prevents the damage to the tooth or the restoration. Coming on to the strength properties, strength can be defined as the maximum stress that the structure can withstand without sustaining a specific amount of plastic strain, or the yield strength. Stress at a point of fracture is known as your ultimate strength. The point from which your fracture tends to occur, the stress at the point of fracture is known as your ultimate strength. So when we describe the strength of a material, we are most often referring to the maximum strength that is required to cause a fracture of a material. Strength of the material can be defined as the proportional limit, elastic limit, yield strength or ultimate tensile strength, shear strength, compressive strength and the flexural strength. Coming on to the proportional limit, it is defined as the magnitude of the elastic stress above which plastic deformations take place. See, elastic stress, it is the magnitude of the elastic stress above which plastic deformation means that when you apply a force on an object, it tends to deform. When you remove the pressure, when you remove the force from the same object, it will never come back to its original shape. It will completely deform, permanently deform. So as stress is increased, the strain is also increased. So can you see this? The elastic, when you apply a force, it gets to a normal, you can say a normal shape. But when you apply the plastic deformation, can you see this? The plastic deformation takes place once you remove the force. It will get permanently deformed. It will never come back to its original shape and form. So initial, at the zero, a portion that the stress is linearly proportional to the strain. A strain is double. When the strain is double, the stress is also doubled. After the point A, the stress is no longer linearly proportional to strain. Here the value of A is known as the proportional limit. So it is also defined as the highest stress at which the stress strain curve is nearly a straight line. That is the stress is linearly proportional to the strain. Below the proportional limit, there is no permanent deformation in the structure. That is, the object will return to its original dimension because it is an elastic deformation. And after your A point, after your proportional limit, it is the plastic deformation. When you remove the forces, it will never tend back to its normal position or normal shape. It gets permanently deformed. So the material is elastic in nature below the proportional limit. Below the proportional limit, it is from here to here, from 0 to 60, it is proportional in limit. The region of stress strain curve before proportional limit is known as your elastic region, and beyond point A, it is your plastic deformation or plastic region. So when a material is said to have high value of proportional limit, it indicates that the material which is most likely to withstand the applied stress without getting permanent deformation. That's why your connectors in your prostho, in your connectors are mainly made up of your cobalt chromium, because it has the highest proportional limit and it is basically used for the fabrication of connector because they withstand with the higher stresses without any permanent deformation. Coming on to the elastic limit, defined as the maximum stress that a material withstands without permanent deformation, as I've already told you. For linearly elastic materials, the proportional limit and the elastic limit represents the same within the structure. Coming on to the yield strength, it is defined as the stress at which a test specimen exhibits a specific amount of plastic strain, that is, a specific amount of deformation. It is a property that represents a stress value at which a small amount of plastic strain can occur. It is a property often used to describe a stress at which the material begins to function in a plastic manner. It means the material is getting deformed. The amount of permanent strain is referred to as percent offset. So a value of either 0.1% or 0.2% of the plastic strain is often selected and referred to as percent offset. The point at which at the parallel line intersect the stress strain curve, it is known as your yield strength. Can you see that this is your 0.2% of offset of the plastic strain? So the elastic limit, proportional limit, yield strength are defined differently, but their values are fairly close to each other in many cases. So this is your elastic region, this is your plastic region, this is your proportional limit, your yield strength, and this is your ultimate tensile strength, and this is your 0.2% of offset, is the parallel. So these values are important in the evaluation of the dental materials because they represent the stress at which permanent deformation begins. If the values are exceeded by the masticatory stresses, the restoration or the appliance may no longer function as the originally designed. Also, a FPT becomes permanently deformed through the application of excessive occlusal forces. Since a stress equal to or greater than the yield strength is developed, and it becomes, and the bending, or you can say the flexural stress become more prominent in your FPTs. So in a process of shaping an orthodontic appliance or adjusting a clasp of and removable partial denture, it is necessary to apply a stress into the structure in the excess of the yield strength if the material is to be permanently bent or adapted. So when you adapting a clasp, whether it is Adams clasp or C clasp or your crozet clasp, because clasp is basically used to provide the retention in your denture in your removable appliances. So when you apply the force, when you apply any stress onto the structure, you can apply at its proportional limit. The proportional limit it is the point at which it is the end of the elastic strain and the beginning of your plastic strain. So ultimate strength is defined as the maximum stress that a material can withstand before failure in tension. Ultimate compressive strength is the maximum stress that a material can withstand in compression. It is a ultimate compressive stress. The ultimate strength or the stress is determined by dividing the maximum load in the tension by original cross-sectional area of the test specimen. So the mechanical properties based on the plastic deformation. If a material is deformed by the stress at a point above the proportional limit before fracture and upon removal of the applied force, the stress will reduce to zero, but the deformation remains. It means when you apply any force above to the proportional limit, because in the proportional limit, when you remove the within the proportional limit, when you remove the force, the object will get back to its normal position, normal shape and form. But beyond the proportional limit, when you apply the force, the stress will when you reduce the force or when you remove the force, the object will tend to undergo a plastic deformation, or you can say the object gets completely deformed permanently. Thus the object will not return to its original shape. When the force is removed, it remains bent, stretched or compressed, that is, it becomes plastically deformed. As I've already told you, that when you apply the pressure within the proportional limit, it will never get distorted, never get deformed. When you apply the force beyond the proportional limit, the object tends to get deformed and will never return back to its original shape. So coming on to the cold working, that is also known as strain hardening or work hardening. When the metals are stretched beyond the proportional limit, hardness and the strength increases at the area of deformation, but their ductility decreases. Very important. Repeated plastic deformations of the metal during bending of the orthodontic wire can lead to brittleness of the deformed area of the wire, which may fracture on the further adjustment. When you adjusted a clasp or giving a bend continuously in a different direction, what will happen? At a certain beyond the proportional limit, beyond this proportional limit, at the plastic deformation, it get fracture from the side where the force is applied. So to minimize the risk of brittleness is to deform the metal in the small increments so that it plastically deform the metal excessively, so as not to plastically deform the metal excessively. So to minimize this, what you have to do is you just deform the metal in the small increments by not applying a sharp bend or a sharp force. So flexural strength defined flexural, as I already told you, that it is flexural stress, or the flexural strength is also known as bending. So it is defined as the force per unit area at a constant fracture in a test specimen which is subjected to flexural loading, that is known as your bending. It is also known as modulus of rupture. It is a strength test of a bar supported at each end under a static load. So coming on to the flexural strength for a bar with a rectangular cross section, it is subjected to 3-point flexure. The flexural strength can be calculated as your maximum flexural stress, your load at the fracture, and your distance between the two supports divided by the width and the thickness of the specimen. So these are the supporting pin, this is the specimen, this is the loading pin. When you apply the force, what will gonna happen? The flexural strength, it will get bending down. In your FPD, 3-unit FPD and 2-unit FPD, you can generally see the flexural strength or the flexure strain. So the most prosthesis and the restoration fractures develop progressively over many stresses cycle after initiation of a crack from a critical flow, and subsequently by propagation of a crack until a sudden unexpected fracture occurs. This phenomena is known as your fatigue failure. And can you see this? This is the fracture and this is the fatigue failure. Coming on to the impact strength, it is defined as the energy required to fracture a material under an impact force, measured using a Charpy impact tester where a pendulum is released that swings down to the fracture. The center of the specimen supported at both the end. This is the pendulum. It is released that swings down to the fracture. This is the pendulum. A moving object poses at a kinetic energy. This is the specimen. pendulum is the end of the swing and the starting point, that is the hammer. If a struck object is not permanently deformed, it stores the energy of collision in an elastic manner. This ability is due to resilience of a material and is measured by the area under the elastic region of the stress-strain curve. Thus, a material with a low elastic modulus and a high tensile strength is more resistant to impact forces. Therefore, a material with a low elastic modulus and low tensile strength has the low impact resistance. Very important points. This is the elastic modulus and tensile strength of the composite porcelain amalgam. Please go through it once. Coming on to the toughness, it is the ability of a material to absorb elastic energy and to deform the plastically before fracturing. Measured as a total area under a plot of tensile strength versus the strain. It can be defined as the amount of elastic and the plastic deformation energy required to fracture a material. How much energy is required to fracture a material? So toughness increases and your toughness increases with the increase in the strength and the ductility. Obviously, that is, greater the strength and higher is the ductility, the greater is its toughness. Example, the rock, or you can say the large stone. Fracture toughness, it is a mechanical property that describes the resistance of the brittle materials to the propagation of the flows under applied stress. The longer the flow, the lower is the stress needed to cause fracture. This is because the stress which would normally be supported by the material are now concentrated at the tip of the flow from where it begins. So the ability of the flow to cause the fracture depends on the fracture toughness of the material. So the fracture toughness is a material property and is proportional to the energy consumed in the plastic deformation before it gets deformed. This is the material and the fracture toughnesses. The enamel 0.7 to 1.3, dentine ranges from 3.1, amalgam 1.3 to 1.6, ceramic 1.2 to 3, composite 1.4 to 2.3, porcelain 0.9 to 1. Coming on to the brittleness, it is the relative inability of a material to sustain plastic deformation before fracture of the material occurs. Example, your amalgam, ceramics, composite that are brittle at the oral temperature. They sustain no or little plastic strain before they fracture, that is, the brittle material fracture at or near its proportional limit. Dental material with a low or 0% of elongation, such as in amalgams, composites, ceramics, etc., will have little or no burnishability because they have no plastic deformation potential. Coming on to the ductility, it is the ability of a material to sustain a large permanent deformation under a tensile load up to the point of fracture. Example, a material can be withdrawn readily into long thin wires is said to be ductile. Example is gold. Ductility is a relative ability of a material to stretch plastically at a room temperature without fracturing. You can be drawn into a long thin sheets without fracture. Its magnitude can be assessed by the amount of permanent deformation indicated by the stress-strain curve. Methods to determine the ductility are percent elongation after fracture, the reduction in the area of tensile specimens, maximum number of bends performed in a cold bend test. Coming on to the malleability, it is the ability of a material to sustain considerable permanent deformation without rupture under compression, as it is hammering or rolling into thin sheets. Gold is the most ductile and malleable pure metal, followed by silver. These can be hammered and rolled into sheets, and your ductility is readily drawn into long and thin wires. Coming on to the hardness, it is the resistance of material to plastic deformation, which is typically produced by an indentation force. In mineralogy, the relative hardness of a material is based on the ability to resist scratching. Your best material for the hardness is your diamond. Classification of the hardness test: method of application, size of indenter and the amount of load applied to the indenter, static loading, macro indentation, macro hardness. In this, you can apply the force slowly, large indenter tip, and more than 1 kg of the load. In the dynamic loading, rapidly applied micro indentation causes a small indenter tip, and micro hardness less than 1 kg of load. Very important. Now, various hardness tests includes the Brinell test, the Rockwell, Vickers, and the Knoop test. Coming on to the Brinell test, it is used extensively for determining the hardness of the metals and the metallic material used in the dentistry. So, related to the proportional limit, the ultimate tensile and the ultimate tensile strength. The method depends on the resistance to the penetration of a small steel ball, typically 1.6 mm in diameter, when subjected to a specific load. Method: a hardened steel ball is pressed under a specific load into a polished surface of the material that is to be tested. Okay, the load remains in contact with the material for a fixed time of 30 seconds. After 30 seconds, when the force is removed, the indentation's diameter is measured. So the load value is then divided by the area of projected surface of indentations, and questioned is referred to the Brinell hardness number. This is the Brinell indentations. When you apply the steel ball compressed into a pressure into a polished surface of a material, so you can apply the load for 30 seconds. After removal of 30 seconds of the force, after 30 seconds, if you remove the force, you can see the indentations, and you can measure these indentations. That is known as Brinell hardness number. So since the Brinell test yields a relatively large indentations area, this is a good test for determining the average hardness value and poor for determining very localized value. Thus, for a given load, the smaller the indentations, the larger is the number and harder is the material. Advantages are: it is best suited for testing ductile material, that is the gold. Disadvantage: hardness of the cold work material are difficult to measure, not suitable for brittle materials. Coming on to the Rockwell hardness test. This test was developed as a rapid method for the hardness determinations. Here, instead a steel ball, a conical diamond point is used. Can you see this? A conical diamond point is used. The depth of the penetration is directly measured by a dial gauge on the instrument. The test is not suitable for testing the brittle materials. So the number of the Rockwell hardness, when you apply, so in this, instead of using a ball, you can use a conical diamond burr. So advantages of your Rockwell hardness test is your direct reading of the depth of the indentation and has the rapid testing time. Same way, the disadvantages are: it is not suitable for the brittle material. Coming on to the Vickers hardness test. So this test uses a square base pyramidal indenter. Number one, in this your Brinell test, we are using a steel ball In your Rockwell hardness, we are using a conical diamond point, and in your wicker test, we are using a square base perimeter indenter. So in this, the impression obtained on the material is a square. This method is used similar to Knoop's and the Brinell's test. The load value divided by projected areas of the indentations gives the wicker's hardness number. The length of the diagonals of the indentations are measured and averaged. These you can measure the indentations. Used for testing the dental casting alloys as well as tooth structure. These are suitable for determining the hardness of the brittle material, for example the gold. Advantages: these are useful for measuring the hardness of the small areas and the hard materials. Disadvantages are: materials require highly polished surface, longer time required to complete the test. Coming on to the Knoop's hardness test, it is very important for exam point of view. This test was developed mainly to fulfill the need of a micro indentation test method. It is suitable for testing thin plastic or a metal sheet or the brittle material where the applied force does not exceed up to 35 Newton. Important: the test is designed so that varying load may be applied to the indenting instrument. Therefore, the resulting indentations varies according to the load applied and the nature of material tested. So the impression in this is rhomboid in outline and the length of the largest diagonal is measured. This is the largest diagonal, so the length of the largest diagonal is measured. The load value is then divided by the projected areas to get the Knoop hardness number. So it is useful for very brittle materials or thin sheets. The disadvantages are: material requires highly polished surface as that of your previous one, longer time required to complete the test. So this is the material and the Knoop hardness. Enamel having the 343, dentine has 68, cementum is having 40, denture acrylic 21, zinc phosphate cement 38, porcelain 640. So I have a question regarding this. Hardness, an MCQ. Hardness number which does not depend on the ductility of the material. The answer is Knoop hardness number. Coming on the stress concentration effects, the cause of the strength reduction is the presence of small microscopic flaws or the microstructural defects on the surface or within the internal structure. These flaws are especially critical in the brittle materials in areas of tensile stress because the tensile stress tends to open cracks. So stress at the tip of these flaws is greatly increased, which leads to crack initiation and the broken bond. This is the brittle material. These are the flaws. Can you see the crack? It is in the initial areas at the tips, you can see. You can apply the tensile force, and these are the flaws, and you get the crack at the tips or the initial areas. So when a brittle or a ductile material is subjected to compressive stress, it tends to close the crack, and this stress distribution is more uniform. Can you see this? But when a ductile material is subjected to a tensile force, it tends to opening of the flaws, and from the opening of the flaws it gets plastically deformed and leading to crack formation. So two important aspects of the flaws: the stress intensity increases with the length of the flaws. Second is the flaws on the surface are associated with the higher stresses than flaws of the same size in the interior region. Therefore, the surface of the brittle materials such as the ceramics, amalgams are extremely important in the area subjected to tensile strength, because in this area, in the amalgam or the ceramics, we tends to see the cracks or the flaws. From the flaws we can see the creep in the amalgam restoration and your cracks in your ceramics and the amalgam. Coming on to the causes for the areas of the high stress concentration and the method to minimize them. Surface defects such as the porosity or the grinding roughness in this polysurface to reduce the depth of the defects. So interior flaws such as the voids, little can be done about the interior flaws but to ensure highest quality of the structure or to increase the size of the object. Marked change in the contour, sharp internal angles at the axiopulpal line angle. So design of the prosthesis, it can be corrected by the design of the prosthesis should vary gradually then abruptly. Notches should be avoided and all the internal line angles should be rounded. It is very important. So a large difference in the elastic of modulus or the thermal expansion coefficient of the thermal expansion across the bonded surface. So to overcome this, the elastic of modulus of the two materials should be closely matched. The material must be closely matched in their coefficient of expansion or contraction. So a Hertzian load, a load applied to a point on a surface of a brittle material. To overcome this, a cusp tip of an opposing crown or the tooth should be well rounded such that the occlusal contact area of material is large. So before ending, I have some important MCQs regarding the physical properties. The first MCQ is the stress is defined as an internal force opposing an applied load. The strain is, next MCQ is, the strain is defined as a deformation resulting from an applied force. These both MCQs were there in your EAMS exam. So as I've already told you that the hardness number which does not depend on the ductility of the metal is your Knoop hardness number. Next, as I've already told you, the Brinell hardness number of the dental gold alloy is directly proportional to the tensile strength. I repeat the MCQ. The Brinell hardness number of a dental gold alloy is directly proportional to the tensile strength. Next MCQ, ultimate tensile strength refers to the stress before fracture. It was there in your AIPG exam. Ultimate tensile stress refers to the stress before rupture. Next MCQ, when the solid gets wet completely, the contact angle is, your answer is 0 degree. Next MCQ is coefficient of thermal expansion of gold inlay is similar to the tooth. I repeat the MCQ. The coefficient of thermal expansion of gold inlay is similar to the tooth. It was there in your EAMS exam. So flow of the material refers to your next MCQ. The flow of the material is refers to the continuous change of the material under a given load. Next MCQ is creep is time independent. Next question, Knoop hardness test is a, your answer is micro hardness test. There were several questions in your previous exam from the Knoop hardness number. Next MCQ, Knoop hardness number of enamel is close to, your answer is porcelain. Next MCQ, the Brazilian test is used to determine the ultimate tensile strength of the brittle material. I repeat, the Brazilian test is used to determine the ultimate tensile strength of? Your answer is the brittle material. Next MCQ is the angles between the adhesive and the adherent is 0 degree, which indicates your answer is complete wetting of the surface. Next MCQ is coefficient of thermal expansion of the tooth enamel is closest to? Your answer is glass ionomer cement, that is GIC. It was there in your AIMS exam. Next MCQ is the molecule with a permanent dipole. Your answer is the water. I repeat the MCQ, the molecule with a permanent dipole. Your answer is water. Your next MCQ is the type of strain developed when a force is applied perpendicular to the surface is? Your answer is compressive strain. This question was there in your AIMS exam. I repeat the question. The type of strain develops when the force is applied perpendicular to the surface. Your answer is compressive strain. Next MCQ, the ductility represents the percent elongation. I repeat, ductility represents the percentage elongation. The percent elongation. It was there in your AIPG exam. Stiffness is, your next MCQ is, stiffness is resistance to elastic deformation. I repeat, stiffness is resistance to elastic deformation. It was there in your AIMS exam. So your last MCQ is a wetting agent enhances. A wetting agent enhances. Your answer is adhesion. So this is all about your physical properties of dental material. Please go through it once. Thank you.